Good afternoon, ladies and gentlemen. Thank you so much for joining us today at the session in regards to oil spill mitigation. We're going to be starting shortly. We just wanted to kind of go over a little bit of a housekeeping rules for today's session. All of you will actually be muted at this point, and we would love for you to hold your questions at the end of the session. If after the session is over, we're going to open it for Q&As, and you can either ask question by raising your hand, and then I'll give you permission to unmute yourself, or you can just type in your question in Q&A box. Before we do that, though, I will be launching a poll, and we would love for you to quickly fill it out. It takes no longer than 30 seconds, but we would love for you to give us an input on what you thought about this presentation. And without further ado, Mr. Venosa, go ahead, and if you wouldn't mind introducing yourself, that would be fabulous. Thank you so much.
Yes, thank you, Aga. Good afternoon, everyone. Thank you for coming by. My name is Al Venosa, and I used to work for the U.S. Environmental Protection Agency for 45 years. And just a little quick bio on me. I got all three of my degrees from the University of Cincinnati. In 1967, a BS in microbiology, in 1968, MS in environmental engineering, and a PhD in 1980 in environmental science. I began work at EPA in 1968, conducting research on wastewater disinfection, which continued until through 1988. And then in 1989, the Exxon Valdez oil spill occurred. And afterwards, that led to EPA's oil spill research program from 1991 until I retired in 2014. So that's about all there is for me. Oops. The Exxon Valdez oil spill was a game changer for me. It happened in March 24th of 1989. The tanker ran aground in Bly Reef in Prince William Sound, Alaska, released 11 million gallons of Prudhoe Bay crude oil into the sea, and the oil eventually impacted about 1,100 miles of non-continuous coastline. And these are a couple of pictures showing you how devastating that particular spill was. You can see this person is standing, and this is the way it was. I was there, I saw it, and this is just a puddle of crude oil. This is the amount of waste products that were developed in one particular island. There's a few of the birds that were completely oiled, and then this is the aftermath of the waste that was generated. So what I'm going to do today, I'm going to give you an outline. First of all, I'm going to define the problem. Why do we clean up oil spills? Give you a brief familiarization with the petroleum chemistry, so that you have an appreciation for how complex crude oil is and what we have to do to clean it up. The major cleanup options are natural response methods. And then there's the physical, biological, and chemical response methods. Then I'll spend a couple of minutes talking about the toxicity and environmental impacts of spilled oil. And finally, if we have time at the end, I've got 3 or 4 slides on oil spills of significance since the Exxon Valdez. So the amount of oil that enters into our oceans is estimated to be about 343 million gallons per year. That's a lot of oil. About 46% of it comes from natural seepage from the ocean floor, and we can't do anything about that. We have to live with that. But the secondarily 37% of it comes from spills, and this is a photograph of the ocean floor, and this is that natural seep of crude oil coming through the cracks and so forth in the bottom of the ocean. So what happens to the oil once it's released into our oceans. Well, why aren't we knee deep in oil by now? Well, crude oil is biodegradable, believe it or not. It really is. And so most of the oil disappears in that fashion. But there's other things going on besides biodegradation, and that is evaporation is part of it. This is a slick spreading on the ocean floor. And it's moving in the left to right in this particular slide. Chocolate mousse is what happens when oil mixes with water and air, and it forms a chocolate mousse, which that's what we call it because it looks like mousse. Very difficult to degrade. But there's other things that are impacting oil on the sea surface. It can produce oil and water emulsions. It can dissolve and undergo chemical degradation. But the eventual removal mechanism is biodegradation by microorganisms that convert it into CO2 and water. So why do we clean them up if nature does such a good job? Well, because in most spills, there's a huge volume released in a very small area. And so we need to clean that oil up in order to protect the species, either the birds that are flying into it or the fish below it. And we want to try to improve the ecosystem so that those organisms can live. This is a picture of an accident where a ship was broken in half, releasing oil. So by 1940, it's been estimated that we'll still be using oil, crude oil, for 27% of our energy supply. And as you can see here, we've got oil, we've got coal and natural gas making up about 75% of our usage, even into the 1940s. So it's going to be here for a while. Now, so let me give you a brief familiarization with oil chemistry. There's 4 major classes of compounds, and we use an acronym to describe them, SARA. The first S is for saturates. I'll explain to you what that word means in a minute. The next one is aromatics. The next one is resins. And finally, the second A is asphaltenes. Saturates basically are alkanes, alkenes, and so on. They're the major component of petroleum. They're comprised of hydrocarbon molecules with single carbon bonds or double carbon bonds, with all the remaining bonds being saturated with hydrogen atoms. That's what saturation means. That's why we call them saturates. So the normal alkanes, the most simple one is methane, 1 carbon, 4 hydrogens. And then there's ethane with 2 carbons and 6 hydrogens. Propane is 3 carbons and so on, up to many, many more than heptadecane is 17 carbons with 36 hydrogens. It's a linear molecule. Then we have branched alkanes. As you can see, we have down here at the bottom, we have the straight chain, but also we have branches coming off of it, which increases the complexity of the molecule. And it's a little bit harder for microorganisms to degrade because they have to deal with these branches. So this is pristane and this is phytane. And then there was the aromatics, the A in SARA, the first A. They're cyclic unsaturated compounds, meaning they're not fully saturated with a bunch of hydrogen atoms. They have the structures based on a single benzene ring or multiple fused benzene rings. So for example, the MAHs, the monoaromatic hydrocarbons, are composed of benzene or toluene, ethylbenzene, and xylene. Benzene is the simplest one, very toxic, very carcinogenic. Toluene is the same as benzene, except it's got an extra carbon coming off of it. Ethylbenzene has 2 carbons coming off of it. And xylene also has 2 carbons, but they're attached to different carbons on the benzene ring. So those are the MAHs. And that's what makes up gasoline. Basically, those four compounds are the composition of gasoline. The PAHs are the polycyclic aromatic hydrocarbons. These are the benzene rings fused together. So when you have two of them, it's called naphthalene, with a little methyl group coming off of it. That's methyl naphthalene. And then here we have 5 fused benzene rings together. That's called benzoapyrene. It's a compound that is carcinogenic and mutagenic. Then we have the R in SARA, which is the resins, and the NSO compounds. NSO stands for nitrogen, sulfur, and oxygen. These compounds are persistent, they're toxic in the environment, and they give oil its tackifying effect, its stickiness. They're resistant to biodegradation, they're not water soluble, and this is a typical structure. And here you can see there's a sulfur group here, there's a nitrogen, there's an oxygen. These are NSO compound. These are very, very difficult to biodegrade. And then we have the asphaltenes, and as you can obviously guess, this is where we get our blacktop from, our asphalt. Persistent, large compounds, but environmentally benign. They give oil its black color, but they're relatively non-toxic. They're resistant to biodegradation, and this is the typical structure. You can see how complex the asphaltenes are. They're out there for a long, long time. So what are our cleanup options? The primary response options that we utilize, the first one is natural recovery, and that includes natural attenuation, which I'll be discussing in a moment, evaporation, photooxidation, and biodegradation. I'll be talking about them in great detail in a few moments. Then there's the physical response methods that we use, containment and recovery, and in situ burning. In situ is a Latin word meaning in place. So we burn it while it's floating on the ocean. And then there's biological remediation techniques, bioremediation and phytoremediation. Phyto means plant. So once the oil gets into wetlands and so on, then phytoremediation takes place. And then finally, chemical techniques using dispersants, solidifiers, and herding agents. I'll be talking about dispersants a little later. Okay, so on evaporation, when exposed to the atmosphere, the lighter weight, higher vapor pressure components, like the gasoline components, the MAHs, they get removed relatively rapidly. Up to 50% of the more toxic, lighter weight compounds evaporate within the first 12 to 24 hours after the spill. Then there's photooxidation, in which happens when oxygen in the air under sunlight reacts with the aromatic oil components. The oxygen content in the oil increases as sunlight exposure is prolonged, and oxygenated forms increase solubility, the dispersibility, and toxicity of the oil. Then there's monitored natural attenuation. Natural attenuation means that it's a no response action. We just let nature degrade the oil, but we monitor it. That's why it's monitored natural attenuation. That's why it's called MNA, because we have to monitor it and make sure that it's going away as quickly as is possible. This may be the best alternative. Doing nothing may be the best alternative in certain environments where human intervention would actually result in more harm than good, such as trampling on wetlands, for example, or in mangroves. The primary mechanism of MNA is biodegradation, which I'll be discussing in a few moments. In terms of physical methods, booms are the first thing. You see these on TV when you see when there's a discussion of a recent spill. They're placed across a narrow entrance to a larger mass of water. to prevent the oil from passing into sensitive habitats. Their effective operational range is limited by rough water and winds. If the weather is too rough, then the oil will go over the booms or under the booms, and they're not very effective that way. Skimmers are used, whereas we've got basically booms that are attached to boats. And so then they drag the oil so that they can concentrate it, collect it, separate it from water. We release the water back into the water, and we take the oil and we save it for later recovery. Then we have sorbents. These are, as you can see, there's a bunch of sorbent pads here, and this is called sausage boom. It's not really a boom. It looks like a boom because of its structure, but it's really nothing more than a sorbent. And they can be used again to protect bays and so on, and absorb the oil that's going into them. Here's a picture of people applying peat moss to a shoreline to minimize exposure to fur and feathers of animals, for example, penguins and seals. And then there's manual removal from shorelines. Before cleanup, we have to remove the pools of oil, the free product that obviously happened during the initial spill. And once that does, then you can start using scraping, bagging, trenching, and so on. As you can see, it's very, very labor intensive. A lot of people involved, and it's not fully effective. Then we have low and high pressure washing. Both were used in the Exxon Valdez oil spill. They tried high pressure, high temperature washing, and that was a disaster. The high temperature kills off a lot of wildlife. So they went to using cold water, high pressure cleaning. As you can see the picture down here, you can see a bunch of people who are applying high pressure washing of a particular shoreline in Prince William Sound. So this approach is when you use cold water, it's less damaging to the flora and fauna than other methods, and it's effective as well. Then we have in situ burning. We can actually burn the oil on the sea, and the purpose is to rapidly reduce the mass of the oil spilled at the site. It's a controlled burn, and it's been validated as an operational spill response countermeasure following its success during the Deepwater Horizon spill. I'll be talking about that later as well, but I got a few pictures of them here. You can see that. You don't want to be downwind from an in situ burn because these clouds of smoke coming off from the oil that's being burned contain toxic chemicals, and you don't want to breathe that in. But the oil has to be thick enough so that it can burn. And in order to do that, that's why we put fire-resistant boom, and we pull that boom with a boat to concentrate the oil to be thick enough so that it can be lit and burned. Okay, so let's talk about the science-based methodologies. The first one is biological remediation methods. What is bioremediation? It's basically defined as the exploitation of living microorganisms converting organic matter, organic contaminants into biomass and innocuous end products. And these innocuous end products include carbon dioxide, water, and incompletely oxidized organics that are relatively innocuous to living things. Now, the composition of living matter, among all the things that we, animals and humans and everything else on this planet are made of, are carbon, nitrogen, and phosphorus. Those are the three primary compounds of life. Carbon is the basic structural component of protoplasm and biomolecules. Nitrogen is used in the formation of amino acids for protein synthesis, and phosphorus is used in the formation of genetic material, DNA and RNA, and high energy bonds and membranes. Those are the three basic components of life on this planet. So the process of biodegradation of oil consists, these are the steps. The first step is oxidation. The introduction, what that means, it's the introduction of oxygen in the form of an OH group to form an alcohol. So that's what happens when, in the first step of oxidation, is the formation of an alkane alcohol, or the addition of oxygen to a PAH ring to form an alcohol. Once that alcohol is formed, then it oxidizes further into aldehydes and finally carboxylic acids. And once that happens, then the microorganisms can cut off 2 carbons at a time. And then that's how we get chain length reduction. In the case of PAHs, ring fission has to occur first. In other words, those benzene rings have to open up and become linear before the microorganisms can degrade it further. Once that happens, then oxidation is followed by chain length reduction, as it is for alkanes. So what are the requirements for successful bioremediation? We have to have bacteria that are metabolic, that have with metabolic capabilities, and they have to be present. The rates of growth can be maximized by ensuring that there's an adequate supply of oxygen and nutrients present at the site, and the pH should be no less than 6 and no greater than 9, a relative neutrality in pH. The weight of oil, the lighter oils are more biodegradable. Asphaltenes are the heaviest, as I mentioned before. They inhibit diffusion of biodegradable components to the bacteria. The oil surface area is important because biodegradation occurs mostly at the oil-water interface. So where are oil degraders found? Well, hydrocarbons are found everywhere on this planet, everywhere that we've ever looked, whether it's Antarctica, whether it's the hottest part of the oceans, everywhere, the oceans, the land, and so on, hydrocarbons are found. You can go in your backyard and put your hand in your soil and you'll find oil degraders in it. Hydrocarbon degraders are also found everywhere. Everywhere we've looked, we've found hydrocarbon degraders. So an oil spill suddenly causes a huge influx of carbon, which is food. So how do the bacteria cope with this sudden influx of food into the environment? Well, to convert carbon to biomass, bacteria must have nitrogen and phosphorus, which are the essential nutrients for life, as I mentioned a couple of slides ago. Bacteria will grow slowly in the presence of the usual amounts of N and P in nature. That's why we fertilize our lawn, because there's not enough nitrogen and phosphorus there normally to allow a growth of a good lawn, a good stand of lawn. So to maximize the rate of growth, you must have to add, you must have more N and P to allow the organisms to degrade rapidly. So there's 2 processes of bioremediation. There's what we call biostimulation, which is the addition of factors, usually nutrients, that normally limit the degrading populations to grow at their normal maximum rate. The other one is bioaugmentation, where you add a highly competent microbial culture grown in the lab to an impacted site to accelerate degradation process. So the assumptions for successful bioaugmentation are that the culture must be able to grow rapidly on the oil, obviously, and the culture must be able to colonize the environment rapidly and outcompete the natural communities present. So they have to, if you grow them in the lab and then bring them out to the field, they have to outcompete the natural populations that are already there. So the question then is, what have we learned so far? Oil degraders are everywhere. We know that. And bacteria need N and P to convert oil to biomass, nitrogen and phosphorus. So the second question is, how necessary then is it to add oil degraders to an oil spill to augment the existing populations to degrade it? The answer is, it's ineffective for oil spills. You don't need to add organisms to the existing populations, because it's going to be very difficult, no matter how good they are in the lab, to overcompete with those populations. Why is this? Because the natural concentrations of N and P are too low to allow rapid biodegradation. In fact, I got this in green here to show how important the scientific literature has shown that there's no evidence that bioaugmentation has ever been successful in helping to degrade hydrocarbons in the field. So if someone comes up and says, I've got this great bug that will degrade oil, don't spend your money. Are the previous facts about bioaugmentation true for all pollutants? Certainly for biohydrocarbons, it is. But for certain types of hazardous waste sites, bioaugmentation could be and often is effective. And we're talking about things like PCBs, polychlorinated biphenyls, chlorinated solvents, dioxin. These are man-made compounds that haven't been on this planet very long. Hydrocarbons have been on this planet for millennia. So hydrocarbon degraders are present everywhere because they use it for food. They use the hydrocarbons for food. But these chlorinated solvents, dioxin, PCBs, and so on, are relatively new compared to the millennia that the hydrocarbons have been present here. So since most man-made chemicals have never been on the planet long enough to allow for the natural development of degraders. Okay, so let's talk about the degradability of the oil constituents. There's the gasoline. Bioremediation is not needed. Why is it not needed? Because they're so volatile, the BTEX compounds, that by the time you get someone, a ship or whatever present to treat the gasoline or the BTEX compounds, they've already evaporated into the air. So there's no need to treat a gasoline spill on the water. Easily degradable oils include diesel, heating oils, light and medium crude oils. Those are relatively easy to degrade. The more difficult ones are the heavy crude oils, the number 6 fuel oil, which is what you use to heat in your furnace, the bunker C, which is what large ships use for its transportation. And then there's vegetable oils and animal fats. Some of them are unsaturated oils. They oxidize and they polymerize. And then they form, and also the saturated oils like palm oil form persistent gumballs that last for decades. There was a palm oil spill back in 1986, I believe, in Britain. I think it was Great Britain. I can't remember quite what city it was in. But those gumballs have persisted, and they're still there 30 years later, 30 or 40 years after that spill. So those particular compounds are not very degradable. Okay, what about the various SARA compounds? The SARA, the saturates, the alkanes, they're easy. They're easy to degrade. The aromatics, the PAHs, they're moderate to difficult. It depends upon the number of rings. If you have one of those rings that I showed you before that have 5 or 6 rings attached to each other, those are very difficult to degrade. Then there's the resins and NSO compounds. They're difficult. The asphaltenes are the most difficult. Okay, so I'm finished with bioremediation. Now let's turn our attention to chemical remediation. In fact, I'm going to be talking mostly about dispersants. What is dispersion? It's the conversion of spilled oil on the sea surface into tiny oil droplets that stay in the water column and dilute to very low levels. We want to dilute the oil because we don't want the fish or the ducks that or the flying organisms to get it into their feathers. Dispersion is a natural process promoted by wave energy. You have to have wave energy in order for dispersion to be effective. Natural dispersion occurs, but it's very slow, and it stops due to changes in the physical nature of oil from natural weathering processes. The basis for chemical dispersion use. The process is based on enhanced transfer of oil from the sea surface into the water column as small oil droplets. And this is a picture showing that happening on this particular photo. Droplets are diluted by natural processes to concentrations below the toxicity threshold limits for wildlife. Dispersed oil droplets are biodegraded more rapidly by the bacteria. And we're not hiding the oil. The oil is being diluted to eliminate its toxicity. So what are dispersants? Dispersants are chemicals. They're liquid solutions of detergent-like compounds, which we call surfactants, or surface washing agents, dissolved or suspended in a solvent. So there's two components. There's the surfactants, and then there's the solvent. Detergent-like compounds have two ends. There's a hydrophilic end, which is attracted to the water, and there's the lipophilic end, or the oleophilic end, which is attracted to the oil. And this is a cartoon. This is the hydrophilic end, and a stick is showing the oleophilic end. The solvent then reduces the viscosity of the oil. So that's a big help. The surfactants then reduce the surface tension of the oil-water interface, which allows the oil to enter the water as tiny droplets. The droplets eventually get biodegraded by microorganisms, as I mentioned before. So the properties of dispersants, dispersants reduce the surface tension of water and the viscosity of the oil. The dispersant to oil ratio, the DOR, is best set at 1 to 25 to 1 to 50 by volume. So 1 part of dispersant to 25 to 50 parts of oil is the best ratio, DOR to use for dispersing oil. The salinity of the water is important. The higher, the better. You can't disperse oil in fresh water. It's not very effective. You have to have the salinity to help disperse the oil. The properties of oil that make it amenable to dispersion include its viscosity. The lower the viscosity, the easier it is to disperse. The weight, in other words, the lower the weight, the lighter it is, the hydrocarbons are, the easier they are to disperse. And then the thickness, the thinner of the oil, the better it is. The mixing energy is due to wave action. Is required for effectiveness. So you have to have the wave action in order to disperse the oil. So extremely important variable is droplet size. You want to create the tiniest of droplets with your dispersants, because you don't want recoalescence to occur. The larger particles, the larger oil particles can easily recoalesce, and once that happens, they can float back up to the surface. The rise velocity is higher for larger particles, and the biodegradation rate is much better for the smaller particles. That's why we want to get them to as small a droplet as possible so that they can degrade as rapidly as possible. The droplet size is usually in the range of maybe 60 to 70 micrometers. are neutrally buoyant, and they're associated with chemically dispersed oil. So that's really what we want to achieve with dispersants, is oil droplets that are in that particular range of size. Another cartoon here. This is the dispersant with the surfactant in it. The hydrophilic head is the one that's attracted to the water, the oleophilic tail, and you can see they orient themselves on an oil droplet with the oleophilic tail inside the oil and the hydrophilic part on the surface. So we have a dispersant being added to an oil slick on the ocean. The surfactant locates at the interface. The oil slick is broken into droplets, and then the droplets get dispersed by energy and get diluted out. So we have, this is another diagram showing what happens when we add dispersants to water, to oil floating on water. This is the initial creation of the droplets. This is actually where the attachment occurs between the surfactant and the oil droplets. And then the bacteria start to colonize on these droplets of oil. And then the degradation takes place. And finally, at the very end, once the degradation is complete, then the bacteria that were responsible for degrading the oil then get eaten up by the protozoans and the nematodes. And this is a photograph, several photographs of the EPA got together with Department of Fisheries and Oceans Canada, and we built a wave tank to study dispersion of oil on the surface. And we also had at the bottom of the tank, we can introduce oil this way. And this one, and on the left side of this figure, there's oil alone with no dispersant. And you can see that after 5 seconds, it starts to the oil particles start to rise, and then after 10 seconds, they've risen to the surface just about. Whereas on this side, on the right-hand side, we have oil with dispersant. You can see that they're already dispersed pretty well. And at 5 seconds, they're still in the water column, and at 10 seconds, they're still in the water column. So that's really what it looks like when oil and dispersant interact. Okay, size effects. The probability of recoalescence is greater the larger the particles. The rise velocity are greater with larger particles as well. The biodegradation rate is better with the smaller particles, because of the greater surface area. The droplet size is usually between 60 to 70 micrometers in size, in diameter. They're neutrally buoyant, and they're found associated with chemically dispersed oil. Now, wave action produces and submerges the oil droplets into the sea, into the ocean. The larger oil droplets coalesce quickly to form the oil slicks. The dispersed oil droplets will be rapidly diluted by physical processes in the ocean, waves and currents. They do not sink. They stay in the top 10 to 20 meters in the well-mixed zones, what we call it. The concentration of dispersed oil in the water will initially increase as oil is dispersed, but then decrease as the dispersed oil is diluted. So let's talk about the Deepwater Horizon blowout, which happened back in 2010. And this is a photograph of it. It was the largest accidental marine oil spill in the history of petroleum industry, and I believe it still is. April 10th of 2010, the explosion on the Deepwater Horizon drilling rig occurred, and it killed 11 platform workers and injured 17 others. On July 15th, 3 months later, the leak was stopped. Actually, it was a little later than that, but the leak was stopped by capping the wellhead after about almost 5 million barrels. That's a lot of oil. 206 million gallons of light crude oil had been released. The crude oil, it was South Louisiana crude oil, which is a light crude oil. And luckily, it was a light crude oil as opposed to a heavy crude oil. September 19th of 2010, the federal government declared the well effectively dead after successful completion of the relief well. Just some statistics, 4.9 million barrels of oil were discharged. Each day of the next 5 months, the spill would be considered a major incident. That's how bad the oil spill was. 1.8 million gallons of dispersant were used. 411 in situ burns were conducted. About 265,000 barrels of oil were burned. 48,200 responders were present to fight the oil spill. 9,700 vessels were used on the ocean. 127 surveillance aircraft were used. 3.8 million feet of hard boom were deployed, and 9.7 million feet of soft boom were deployed. So it was a tremendous effort. Now the EPA science team was developed, and that's what I was involved in. I didn't go to the Gulf. Instead, I was stationed in headquarters in Washington, D.C. And we formed a science team, and our responsibility was to develop a sampling and monitoring plan for the deep sea injection and surface application of dispersants. So we developed a plan that BP would use to treat the spill. What we did was we called for measurements of the following items. Dispersed oil by fluorometric techniques. Now, oil is fluorescent, so you can use fluorometers to see what's going on in the water. So we asked BP to make sure they measure CDOM, which are the colored dissolved organic matter, and the CTD, which is conductivity, temperature, and depth profiles throughout the profile from the surface down to 1,200 meters where the spill was happening. We also made sure that they measured droplet size distribution, because as I've told you before, droplet size is very important. We wanted to create small droplet sizes with the dispersant. Direct measurements, we wanted them to make of the oil by chemical methods. The GCMS is gas chromatography, mass spectrometry, and dissolved oxygen profile. The hypoxic level was hypoxic, meaning below that level of about 2 milligrams of oxygen per liter, it becomes hypoxic, which means it wouldn't be enough oxygen there to satisfy fish that are living in that particular area of the ocean. So we wanted to make sure that we didn't reach hypoxic levels. That's 2 milligrams per liter, or other people call it 1.4 milliliters per liter. I'll show you a figure on that in a moment. Now, the dispersant volume that's needed depends on the oil flow rate. So we needed to know how much oil was flowing in order to calculate how much dispersant we needed to use. Lisa Jackson was the EPA administrator back in those days, and she had to make decisions on dispersant volume use. Now, as I told you before, the optimum DOR, dispersant to oil ratio, is about a 1 to 25 to 1 to 50. The flow rate of oil, unfortunately, for the first 30 days of the spill, of the blowout, was unknown. There was no way for us to measure that rate. It took a long time for us to measure the rate of release of the oil. The dispersant volume flow was 15,000 gallons per day, but the oil flow originally was thought to be about 210,000 gallons per day, which would give a DOR of 1 to 14, which means we would be using too much dispersant. So, but later, unfortunately, later, well, I should say unfortunately, but anyway, it was 12. We found that they finally determined what the flow rate was coming out of the blowout well. It was 12-fold higher, to a flow of about 2.6 million gallons per day, and which gives us a DOR of about 1 to 174, which is too little dispersant for maximum effectiveness. Remember, we want to use 1 to 25 to 1 to 50. But because of the uncertainty of the ecological effects of adding that much dispersant to the sea, Lisa Jackson decided to maximize our use of dispersants to 15,000 gallons per day. Now, this is a photograph, or not a figure, showing what happens when we were measuring these things that I just mentioned. The black line here is the CDOM fluorescence. I mean, that's what we were treating, in other words. And the red line here is the dissolved oxygen. This dotted red line is the hypoxic threshold, the 1.4 milliliters per liter that we didn't want to be less than. And as you can see, it never was. So luckily, we were not in hypoxia. But as you can see also, at about 1,200 meters depth below the surface of the ocean or of the sea, you have a huge anomaly here of CDOM. In other words, the carbon from the oil was being measured. And at the same time, we saw an anomaly occurring in the dissolved oxygen. That means that oil was being degraded by the bacteria down there, because the oxygen was being used to degrade the oil. Let's talk about the biodegradability of Gulf oil and the dispersant. Lab studies showed that South Louisiana crude oil is easily degradable. It's a light crude oil, easily degradable. Lab studies also documented that the chemical constituents of Corexit 9500, which was the dispersant that were used to fight the oil spill, was also easily degradable, biodegradable. The lab studies were corroborated by the field data, as demonstrated by the previous slide I showed you, where there was an anomaly. There was a decrease in the oxygen, but not enough of a decrease to cause hypoxia. But it indicated that biodegradation was occurring. And then there's genetic evidence that indicated that the bacteria that were present down there at 1,200 meters below the surface had genes known to be involved in oil biodegradation, and they were abundant in the blowout zone. Okay, so I have a few slides to show the toxicity effects of crude oil. Light oils, like the South Louisiana crude, for example, they're rich in light compounds such as the BTEX and the lower molecular weight hydrocarbons, but they're more acutely toxic than medium and heavy oils. They're acutely toxic to fish and wildlife. The heavy fuel oils with high proportions of the 3 to 5 and higher PAH rings are more chronically toxic. Okay, so light oils are acutely toxic. Large 3 to 5 ring PAHs are more chronically toxic. What they do is they disrupt the embryonic development of fish and other organisms, and they have carcinogenic and mutagenic effects, these higher molecular weight compounds in oil. Dilbit is a material that is a very, very heavy material that differs from other oils in its behavior. And if I have time, I'll mention that at the end of the presentation. So a dilbit, has the propensity to sink in freshwater streams where the environment is anaerobic, and that'll become important to you when I get to that part of the presentation a little later. The acute effects of oil spills, the acute effects, that's the immediate effects, is the smothering of birds, shoreline organisms through coating of feathers and fur. There's a destruction of thermal, what it does, it destroys the thermal insulation and the buoyancy of birds and mammals. They're very severely affected by oil spills. There's rapid mortality of algae, invertebrates, and fish caused by the water-soluble and volatile components of oil. And their acute effects are brief due to weathering. The chronic effects are due more to persistent components of oil, the heavier compounds. They cause deformities, slower development in fish and bird embryos, negative impacts on ecological services such as fisheries, beach waters, water supply, and tainting of seawater. Now, there have been reports that dispersants in oil cause synergistic toxicity, but those reports were found to be incorrect. Dispersion simply increases the concentration of oil to which organisms are exposed. Furthermore, on toxicity, dispersants facilitate oil dilution and microbial degradation. Dispersion reduces oil exposure of the surface and shoreline species, but increases the exposure of algae, invertebrates, and fish. Dispersants are moderately toxic when dissolved in water. The key is to minimize risk. The key to minimize risk is to achieve accurate DOR to the oil slicks. We don't want to add too much dispersant. We don't want to add too little. Dispersants and oil together do not cause a synergistic toxicity, a multiplicative toxicity. The potential impacts of deep water oil dispersion at the well blowout remain controversial. The more research is needed to assess the potential impacts of deep water blowouts on fisheries. Okay, let me talk about some recent spills. Actually, they're not more recent than this first one. Here is the Enbridge spill in the Kalamazoo River, which occurred right around the same time as the blowout in the Gulf of Mexico, about 3 months later. The blowout was in April, and this particular Kalamazoo River spill happened 3 months later. There was a pipeline rupture. 6-foot break in the pipeline resulted in the second largest inland oil spill in U.S. history. The pipeline can carry dilbit. Now, dilbit is composed of heavy bitumen diluted with lighter petroleum products to facilitate the transport of the compounds through the pipeline. So you've got the source of bitumen was from the Canada's Athabasca tar sands. It's very, very thick. It doesn't flow very well. So that's why light hydrocarbons are added to it so that it can be transported by pipeline. That's how we come up with the word dilbit, diluted bitumen. So what happened then during the spill is that the light hydrocarbons in the dilbit evaporated quickly. And that left the heavy bitumen, which then sunk to the sediment. And this is a freshwater spill, so you couldn't use dispersants. It was about 40 miles of river were closed for cleanup. 4,435 acres of riverbank were contaminated. The sediment was very difficult to clean, and the biodegradation was very slow due to the lack of oxygen at depth and the weight of the oil. So we got a couple of things that are working very, very much against us in terms of cleanup. The EPA estimated that the spill released about 1 million gallons of dilbit to the river. And by November of 2014, the cleanup costs amounted to about $1.2 billion. Now then there's this Taylor spill in the Gulf of Mexico. And this occurred, if you look at the picture down here, I'm gonna get this out of the way here. This is where this particular spill was occurring. And it's about, I think about 10 miles or so from the site of the Deepwater Horizon incident. This occurred on September of 2004, when Hurricane Ivan destroyed an oil rig platform located about 11 miles from south of Louisiana. It was spilling 800 to 4,500 gallons per day for many years. So far, the Taylor spill has spewed an estimated 1.5 to 3.5 million barrels of oil into the Gulf waters, which approximates about the 4 million barrels released from the DWH blowout. That's how big that particular Taylor spill was. And then a much more recent spill occurred in Mauritius, the Mauritius oil spill. A Japanese vessel ran aground on a reef in Mauritius, which is in the Indian Ocean. And this happened in July of 2020. Sometimes scientists have called it the Indian Ocean island's worst ecological disaster. The spilled oil spread over a vast area of endangered corals, affecting fish and other marine life. And the cleanup is occurring now and is estimated to be completed in a few months. Here's a picture at the bottom showing that the ship actually broke in half and sunk. And that ends my presentation. So I appreciate your coming today and listening, and I hope to answer any questions that you might have. Thank you. Aga, are you there?
I'm right here. Just trying to resume my responsibilities as a host. So just give me a second, please.
Okay.
And if we have any questions, please go ahead and raise your hand. If there's any raised hands, we will. Oh, there's one. Just a second, please. Or not. Somebody must have lowered it. But if you have any question, please go ahead and raise your hand. We'll allow you to talk, Mr. McDowell. So sorry, things have changed. Okay, go ahead. Mr. McDowell, go ahead and unmute yourself.
Al, with the diminution in exports of oil from the Middle East and the increase in oil oil production and hence use in the United States, do you see any probability in the longer run that oil spills will be less likely to occur? And in addition to that question is with the decision to extricate ourselves from the pipeline, XL pipeline, what do you think the implications are of that? Are pipelines a better way to carry oil than ships?
Good question, Mike. Nobody can predict what will happen in terms of your first question, what will happen with the amount of oil that's being used and transported today across the Atlantic Ocean from other producers in the Middle East and so on. So, right now we are producing more oil than they are. But to what extent, there haven't been, other than what I mentioned today, there really haven't been very many major oil spills that have occurred since that blowout in the Gulf of Mexico. As far regarding your second question, there's always going to be the possibility that an underground pipeline would break, and that happens. That does happen. I think that's the reason why EPA is so worried about that particular pipeline. And I think Biden, just stopped its. Didn't he just recently stop that pipeline from being further developed? If I'm not mistaken,
Yes.
I think he has.
Yes, he did.
Whether that's a better means of. I think one of the major reasons why there was a lot of interest in that is because when a pipeline break does occur in the XL pipeline, it would be relatively close to the groundwater that people use for drinking. And I think that's the major reason why it's not a very popular means of transporting oil across the U.S. But no matter where the oil gets transported, whether it's on the sea or whether it's in pipelines, there's going to be human accidents. They happen all the time. And that's basically all I have to say about it at this point in time. It's very difficult to predict what's going to happen in the future.
Ladies and gentlemen, I just launched a poll. I hope you have seen that showing on your screen. Please take a couple seconds to complete that for us. We would love to know your feedback on this fabulous presentation. I don't see any additional hands raised or any Q&As coming our way. Mr. Venosa for sure has covered quite a bit of ground on this subject. So we would like to thank him very much for participating as a presenter in our Sun Learning sessions. That definitely took a lot of time and effort to put it together for sure. So once again, thank you so much, Mr. Venosa, for presenting for us today. And to all participants, once more, please fill out our poll and let us know how we did today. I hope everybody has a great day.
Thanks very much.
Thank you.
Thank you.
Bye.